Hello everybody. In the last lesson we have learned about the conservation of energy. This is a quite powerful tool, however there are some restrictions to it. For example, there may be no friction, there may be no external non-conservative forces. However, the law of conservation of energy can also be used if we have a so-called open system. So for example, when we have friction or an engine doing something. To learn how this is done, we will follow a thinking task. On Teams in your folder, you find the sheet Thinking Open System, which is that one. And I'll give you now 15 minutes to solve this task. Okay, probably you're a little bit faster, so maybe you're already done in 5 to 10 minutes. So let's have a look at the solutions. The kinetic energy at the beginning simply is 1/2 mv0 squared. At the final is 1/2 mv final squared. But for v final squared, we can use the law from kinematics, which was given here, that the final velocity squared is the initial velocity squared plus 2 times a times x, or s, and replace it here. So we write v0 squared plus 2as. Let's see what comes out. So this amounts to 1/2 mv0 squared plus 1/2 m times 2 is m times a times s. If we now compare these two formulas, we see that in the beginning we had this term and now that one. So the difference is just m times a times s, which we can write in a more easy way if you remember Newton's law. F equals m times a. So we can write F times S, and F times S, if it's in the same direction, which is the case here, simply is the work. So we can state the following idea. If we have a system where we have external forces or friction, we can say that the final energy still is the initial energy, but we have to add or subtract what we have done. So we have to add or subtract the work that was done to this system. So we can write that as a sentence. The total mechanical energy of an open system is changed by the work done due to an external or non-conservative force. So let's have a look at an example where we can use this system. So we have a car. Let's assume 1,200 kilograms. And this one drives at 54 kilometers per hour, which just is 15 meters per second. So we take easy numbers here. Then the driver hits the brakes. These, so the brakes that apply a force of 7,000 Newton to the car. And the question is, what is the velocity after 10 meters? So of course we could use here Newton's law, get the acceleration, and then with kinematics have this answer. But we are going to use this new technique that we have learned. So we state that the final energy is the initial energy plus or minus the work. Well, did we do work to the car or did we take something away? So here we took something away. So it is minus the work we have done. So let's put in the numbers. The final energy is 1/2 mv final squared. Final velocity is what we are looking for. And the initial energy was 1/2 mv initial squared. What kind of work did we do here? Well, we did 7,000 Newton as a force for 10 meters. And we can resolve, so our final velocity is then 1/2 mv squared, 1,200 kilograms over 2 times 15 meters per second squared minus the work done by the brakes. And then we have to divide that by m/2, so 1,200 kilograms divided by 2, and then take the square root out of it. If you put this to your calculator, you get 10.4, at least I did, meters per second, which roughly is 37.5 kilometers per hour. This example, it's not much easier than Newton's law, but it's just more general and more simple to use. So let's have a look at a second question where things might be even easier. How far will the car in total go until it comes to a full stop? So part B. What is the total braking distance and here again we say the final energy, a new one, is the initial energy minus the work done. We can just say it is F times S. S is what we are looking for. And the final energy, if you want to go to a halt, is 0. Initial energy, still 1/2 mv initial squared minus Fs. And here we can resolve for S, which simply is 1/2 mv initial squared over F. So I put Fs here, this one, first to the left side, and then I divide by F on both sides. Let's put in the numbers. So 1/2 m is 600 kilograms, 15 meters per second as the initial speed, and the 7,000 Newton as the force. And I get this distance of 19.3 meters. And this second example has shown the power of this tool, so many exercises can be solved much more easily using this concept of the open system than using kinematics or Newton's law.